33 hours from now, a coronal mass ejection, traveling at over 1,200 kilometers per second, slams into Earth's magnetic field. One day before the spring equinox, the single worst timing on the calendar. There's a physical effect, documented since 1973, almost never mentioned in public forecasts, that makes equinox storms hit harder than the classification suggests. The system is already stressed from last week. The radiation belts are already above alert thresholds, and NASA is about to send 4 humans beyond that shield for the first time in 50 years. Stay with me, because the number on the forecast is accurate, but also deeply incomplete. Subscribe and follow along, because this story does not end when the shockwave hits on March 19th. The sun is not finished with this cycle. The equinox comes twice every year, and the gap between what space weather forecasts say and what the physics actually means is not closing anytime soon. The next compound event is already forming somewhere on that solar surface. And when it arrives at the wrong moment again, this channel is where you get the full picture. No hype, no hand-waving, just the science they forgot to put in the alert. You are going to want to be here for that. Now let's get into it. Something is coming. Right now, at this moment, a massive cloud of magnetized plasma is tearing through space at over 1,200 kilometers per second, and Earth is directly in its path. The countdown is 33 hours. That's not a lot of time. And here's the thing that should make you stop scrolling. It isn't the size of this storm that's the problem. It's the timing. Because this particular storm chose to arrive at possibly the single worst moment on the calendar, and most of the people responsible for warning you about it aren't telling you why. Let's be clear about what's actually heading our way. A coronal mass ejection, a CME, is essentially a billion-ton bubble of solar material that gets hurled off the sun's surface when magnetic field lines snap and reconnect. When a big one launches in our direction, space weather forecasters issue alerts. Satellite operators go on standby, and sometimes people at high latitudes get a beautiful aurora show. The classification system INU-AA uses. The G scale runs from G1 at the low end to G5 at the extreme. This incoming storm is rated moderate. G2, maybe G3. That sounds manageable. Routine even. People hear moderate solar storm, and they imagine a slightly brighter aurora over Canada and move on with their day. But here's the twist that changes everything. The G scale measures intensity in isolation. It doesn't know what day it is. It doesn't account for what happened last week. And it has absolutely no awareness of the single most important variable in this entire situation, which is that this storm is arriving one day before the spring equinox, right inside what researchers call the equinox window, when something called the Russell-McFerrin effect quietly tilts the physics in the storm's favor. The shield weakens, the geometry changes, and a storm that would behave one way in June behaves like something considerably more aggressive in late March. That's not speculation, that's physics. And we're going to get into exactly why in a few minutes. But first, here's another layer most forecasts are ignoring. This is not the first storm this week. Just days ago, on March 13th and 14th, a separate geomagnetic event rolled through, a G2 with the KP index peaking around 6. That event wasn't catastrophic. It came and went. But Earth's magnetosphere, the magnetic bubble that protects us, didn't fully recover. It hasn't had time to reset. The radiation belts surrounding Earth, those donut-shaped zones of trapped charged particles named after James Van Allen, have been running above alert thresholds for several days. The system is pre-stressed, and now the second strike is incoming. Think of it this way. If someone punches you in the ribs and you haven't caught your breath yet, the second punch lands very differently than it would have on fresh muscle. The physics of a magnetosphere under stress works in a similar way. residual energy in the system, elevated particle flux, reduced capacity to absorb new impacts. Scientists call this magnetospheric memory, and it's a real documented phenomenon in space weather research, not a fringe concept. There's one more thing before we zoom out. The sunspot region that fired this CME, active region 4392, is still facing Earth. It hasn't rotated away. It still carries a complex beta-gamma magnetic configuration, which is the classification used for sunspot groups with tangled opposing polarities and genuine potential for major flares. It fired once this week. It can fire again. And if it fires another CME before this one arrives, there's a scenario studied and documented in the research literature where the second, faster cloud catches the first, merges with it, and delivers what researchers call a cannibal CME, a single amplified shockwave built from two separate events combining in transit. The storm hasn't even arrived yet. The system is already unstable. And somewhere in the back of the forecasting community, a 1970s discovery is quietly explaining why this particular week, out of the entire year, is the worst possible time for any of this to be happening. Let's talk about that. In 1973, two researchers named Christopher Russell and Robert McFerrin published a paper that should have become a cornerstone of every public space weather explanation ever written. It largely didn't. You won't find it in mainstream news articles about solar storms. You won't see it referenced in the NOAA alerts that appear on your weather app. But among the researchers who actually studied geomagnetic activity patterns, the Russell-McFerrin effect is considered foundational, a quiet, structural explanation for something that puzzled scientists for decades. Why do more geomagnetic storms happen near the equinoxes? Here's the insight, explained without the math. The sun constantly streams charged particles outward in all directions. That's the solar wind. Embedded in that solar wind is a magnetic field, carried along with the plasma like a current running through moving water. The orientation of that field, particularly whether it points northward or southward when it reaches Earth, determines how much energy it can transfer into our magnetosphere. A southward pointing field, what scientists call a negative BZ orientation, couples much more efficiently with Earth's own magnetic field. It's like two magnets approaching each other with opposing poles aligned. Instead of repelling, they connect. Energy flows in. Now here's where the geometry becomes interesting. Earth's magnetic axis is tilted relative to its orbital plane. The sun's magnetic field rotates and spirals outward in a pattern called the Parker spiral. And near the equinoxes, around March and September, the geometry of Earth's position and axial tilt means that the incoming solar magnetic field is statistically more likely to arrive in that southward orientation. It isn't that the sun fires stronger events toward us in March. It's that the same event, arriving in March, finds a more favorable angle of attack. The physics of connection improves, the energy transfer increases, and the resulting geomagnetic storm hits harder than it would during the same event in, say, June. Picture it like a lock and key system. During solstices, the geometry is slightly misaligned. The field still connects, but imperfectly. Near equinoxes, the alignment improves. The key fits the lock more cleanly. More energy passes through. And the system on the other side of that lock, Earth's magnetosphere, the radiation belts, the ionosphere, has to absorb more of what the sun is sending. What makes this even more layered is that the Russell-McFerrin effect is not the only mechanism contributing to equinox vulnerability. There's a second, distinct phenomenon called the equinoctial effect, which relates not to magnetic coupling, but to the axial orientation of Earth itself, specifically how Earth's rotational axis aligns with the solar wind flow direction. Both effects operate simultaneously near the equinoxes, and both contribute to the statistical increase in storm activity. Researchers still debate the exact relative contributions of each mechanism, but the consensus is clear. Both effects stack. Their influences overlap, and together they create what amounts to a different regime of space weather near the equinoxes, not slightly worse, not marginally elevated, but genuinely more prone to energetic coupling and stronger than expected outcomes. Decades of historical geomagnetic data support this. When you chart major geomagnetic storm occurrences across the calendar, two peaks emerge with striking consistency, one around March, one around September, both near equinoxes. The signal is strong enough that it isn't noise. It's pattern. It's physics. And it means that a G2 rating issued on March 19th carries context that the same G2 rating issued on June 19th simply does not have. So when forecasters release an alert this week and call this storm moderate, they are technically correct, but they are not telling you the whole story. They are giving you the top speed of the car without mentioning that the road is wet, the tires are worn, and the driver is coming off a previous impact. And that gap between what the scale says and what the physics means is exactly where the risk lives. There is one more layer to the geometry of this problem, and it has to do with what happens when that energy actually makes it through the door. Because what's waiting on the other side of Earth's magnetic shield right now isn't a calm, resting system. It's a radiation environment that has been running hot for days. And the consequences of charging that system further are the part of this story that most people never think about until something stops working. Let's talk about the Van Allen radiation belts, because they're one of the most consequential features of near-Earth space and one of the least discussed in any mainstream solar storm coverage. They are two donut-shaped zones of intensely energetic charged particles, primarily electrons and protons, trapped by Earth's magnetic field and circling the planet at altitudes ranging from roughly 600 kilometers out to about 60,000 kilometers. They aren't static. They swell, compress, and fluctuate with solar activity. And when a geomagnetic storm pushes energy into the magnetosphere, those belts can become dramatically more energetic, sometimes for days after the initial storm has passed. Right now, the 2 million electron-volt electron flux, the measurement used to gauge the energetic particle environment in the outer radiation belt, has been running above alert thresholds for several consecutive days. That's a meaningful number. 2 megavolt electrons are sometimes called killer electrons in the space weather research community because they are energetic enough to penetrate spacecraft shielding and create a process called deep dielectric charging. The electrons don't cause obvious external damage. They accumulate silently inside the insulating materials of satellite electronics, building up an invisible charge until eventually, sometimes hours, sometimes days after the initial storm, they discharge in a sudden burst. That discharge can reset critical systems, corrupt memory, destroy components entirely, or cause anomalous behavior that appears to have no weather-related cause. Satellite operators know this. They have procedures for it. The risk is not news to the people who run the infrastructure, but it is almost entirely invisible to the general public because the failure mode is indirect. A satellite doesn't spectacularly explode. It just starts behaving oddly. A GPS signal drifts. A communication relay drops out. A banking transaction fails to route. The connection between the solar event and the downstream consequence is rarely reported because by the time the anomaly is detected, the storm is already old news. What's significant about this week is that the radiation environment is already primed before the new CME arrives. The outer radiation belt didn't fully relax after the March 13th and 14th event. The killer electron flux has stayed elevated. So when the second CME arrives and injects new energy into the system, it isn't filling an empty tank. It's overfilling one that's already close to the top. The overflow is where the unexpected effects live. And here's something worth saying plainly. The G-scale doesn't measure this at all. The NOAA storm scale is built around the disturbance of Earth's surface magnetic field. Essentially, how much the horizontal component of the field fluctuates during the storm. It's a useful, well-defined metric for certain applications. But it says nothing about electron flux. It says nothing about deep dielectric charging risk. It says nothing about whether the radiation belts were already energized before the storm arrived. So when a news headline says G2 storm, minor impacts expected, that assessment exists in a completely separate measurement universe from the one satellite engineers are actually monitoring. There's a compounding effect in the infrastructure domain that doesn't get nearly enough attention, and it's this. Repeated moderate storms can erode systems more than a single extreme event. It's similar to how a prolonged rainy season with week after week of moderate rainfall can cause more ground saturation and landslide risk than a single massive storm that the drainage system actually handles. The ground becomes saturated, the slopes destabilize, and then a relatively ordinary rainfall event triggers a failure that everyone will describe as sudden and unexpected, even though the conditions for it had been building for weeks. Earth's technological infrastructure faces a version of that same cumulative stress. Ground-induced currents, called GICs, are electrical currents that flow through the ground and into conducting infrastructure like power grids, pipelines, and railway tracks when geomagnetic storms disturb the ionosphere above. A single moderate storm might push a transformer to elevated operating temperature without quite crossing into dangerous territory. A second storm a few days later, before the system has returned to baseline, might push it just a little further. A third might cross a threshold that nobody specifically planned for because the standard risk models assume clean baselines between events. The real danger, in many cases, isn't the biggest storm. It's the third moderate storm in 2 weeks, hitting a system that never fully recovered from the first one. We don't currently have a unified risk index that captures all of this simultaneously. No single number combines CME speed, magnetic field orientation, incoming BZ value, current radiation belt state, magnetospheric recovery status, and seasonal geometry into one actionable alert level. Scientists model each of these variables. They track them carefully. But the non-linear interactions between all of them, the way a stressed magnetosphere responds to a southward-oriented CME during an equinox window after elevated electron flux, that combination isn't cleanly modeled by any operational tool currently in use. Which means the forecast you see on your screen, however carefully it was made, is by definition incomplete. And yet, we are about to send 4 human beings beyond the protective reach of Earth's magnetic field entirely, for the first time in over 50 years. Artemis II is not a distant, abstract mission. It is not a rendering on a NASA press release or a concept animation playing on a screen at a space conference. It is 4 specific human beings: Reed Wiseman, Victor Glover, Christina Koch, and Canadian Space Agency astronaut Jeremy Hansen, who are scheduled to climb into an Orion capsule and fly around the moon and back in approximately 2 weeks. Their names are on a crew manifest. Their families know the launch date, and their trajectory will take them somewhere that no human being has traveled since December of 1972, beyond the protective boundary of Earth's magnetic field, into the radiation environment of interplanetary space, where the rules change in ways that the general public almost never thinks about. Let's establish what that boundary actually means, because this distinction matters enormously, and it almost never gets explained clearly in mainstream coverage. The International Space Station orbits at roughly 400 kilometers above Earth's surface. That altitude is still well inside the magnetosphere, the magnetic bubble generated by Earth's core that extends tens of thousands of kilometers into space in all directions. Astronauts on the ISS are receiving elevated radiation compared to people on the ground, yes. The magnetic field at that altitude is weaker than at the surface, but it still exists. It still deflects a meaningful fraction of the charged particles streaming in from the sun. It still provides a layer of protection that, combined with the station's shielding, keeps cumulative crew radiation exposure within manageable bounds for typical 6-month missions. Beyond the magnetosphere, that protection disappears entirely. In cislunar space, the region between Earth and the Moon, there is no magnetic buffer. There is no atmosphere. There is nothing between the astronaut and the full, unfiltered output of the sun except the hull of the spacecraft. And spacecraft hulls are not built like nuclear reactor containment structures. They are engineering compromises between weight, cost, thermal management, and structural integrity. They block a great deal. They do not block everything. For certain types of solar radiation events, they block far less than you would hope. The specific threat in that environment is called a solar particle event, an SPE. When the sun produces a large X-class flare or launches a fast-moving CME, it can accelerate protons and other charged particles to speeds approaching a significant fraction of the speed of light. These particles are not the slow-moving plasma of the CME bulk. They are relativistic projectiles, and they travel fast enough to arrive at Earth's orbital distance within minutes to hours of the initial solar eruption, long before the main body of the CME cloud reaches us. At Earth's surface, you are shielded from virtually all of them by the combined effect of the magnetosphere above and the atmosphere below. In interplanetary space, those particles arrive at the spacecraft with most of their energy intact. For a large SPE, the radiation exposure inside the vehicle can approach or exceed a crew member's entire career dose limit within a single event lasting just a few hours. NASA is not naive about this. The agency has been studying astronaut radiation exposure since the Mercury program. Artemis crews will carry personal dosimeters, devices that track accumulated dose in real time. Mission controllers at Johnson Space Center will have access to continuous space weather monitoring data from NOAA from the DSCOVR satellite sitting at the L1 Lagrange point between Earth and Sun, and from a network of other monitoring assets. There are detailed, operationally tested procedures for what happens if a radiation alert is issued during a cislunar mission. The crew moves to the most heavily shielded section of the vehicle, typically near the center, surrounded by equipment and supplies that absorb additional radiation. They stay there until the event passes. These are not improvised responses. They are protocols built from decades of research, refined through simulation, and informed by the radiation events that occurred during the Apollo era itself. Apollo experienced several significant solar particle events during the program's operational years. The August 1972 SPE, which occurred between Apollo 16 and Apollo 17, is frequently cited in the radiation risk literature because of its exceptional intensity. Had astronauts been in transit between Earth and the Moon during that event rather than safely between missions, the exposure estimates are sobering. The Apollo program got lucky in ways that its planners partially engineered through careful scheduling and monitoring, and partially just got lucky. So the infrastructure for managing this risk exists. The awareness is real. The protocols are in place. All of that is true and worth acknowledging. And yet, we are currently in a period of solar activity that has outperformed every major predictive model. Solar cycle 25 was forecast to be a modest, relatively quiet cycle, a recovery from the weak cycle 24 that preceded it. The consensus prediction put the cycle's peak sunspot number at around 115. The actual peak came in at approximately 161. That is not a small forecasting error. That is a 40% overshoot. The cycle produced more major flares, more fast CMEs, more geomagnetic storm events, and more radiation-significant solar particle events than the pre-cycle models suggested it would. And critically, it has not clearly entered its declining phase. Solar maximum is not a clean peak, followed by an immediate descent. It is a plateau, sometimes a plateau with multiple local maxima, and the transition towards solar minimum is gradual and irregular. The cycle is still producing. Active regions are still emerging. The sun that fired this week's CME is the same sun that has been running hotter and more unpredictably than anticipated for the last 2 years. The equinox window compounds this. The same Russell-McLaren geometry that makes incoming CMEs more geo-effective near the equinox, the improved magnetic coupling, the increased probability of southward IMF orientation, the higher statistical likelihood of storm escalation, also means that this is the period of the year when solar activity translates most efficiently into geomagnetic disturbance. It is the window when a given level of solar output produces the maximum downstream effect at Earth. Artemis II is launching into the equinox window of an overperforming solar cycle, 2 weeks after a sequence of compound geomagnetic events that left the radiation environment above alert thresholds. Each of those individual facts is, on its own, a planning variable. Together, they form a context that deserves more public discussion than it is currently receiving. The question of whether the mission timeline should be adjusted based on dynamic solar activity is not one that casual outside observers are positioned to answer. The radiation risk modeling done by NASA's space medicine teams is sophisticated, built on decades of data, and informed by physical constraints and mission architecture details that are not publicly available in full. The people making these decisions are not ignoring the sun. They are watching it more carefully than almost anyone else on the planet. But the question itself is legitimate. Some researchers, speaking in professional rather than alarmist terms, have noted that solar cycle phase and seasonal activity windows are genuine inputs to human spaceflight risk assessments beyond low Earth orbit. The current alignment of a high-activity cycle, an equinox window, and a sequence of compound storm events is not a combination that appears frequently in the historical record. Whether it crosses any specific mission risk threshold is a determination for the engineers and flight surgeons and mission planners. The point, for the rest of us watching from the ground, is simply that these two stories, the space weather story and the Artemis II story, are not separate. They are the same story, unfolding on the same timeline, involving the same sun during the same unusual solar cycle moment. Those 4 astronauts are going somewhere humans haven't been in more than 50 years. They are doing it during one of the most active solar periods in recent memory. They are doing it during the season when Earth's own magnetic geometry makes the sun's output most effectively dangerous. And they are doing it 2 weeks after the sun demonstrated, twice in 1 week, that active region 4392 is not finished speaking. That is not a reason to ground the mission. It is not an argument for fear. It is a reason to hold both things in your mind simultaneously: the genuine achievement of human beings returning to deep space, and the genuine physics-based reality of what deep space asks of the bodies that go there. The shield that has protected every living thing on this planet for 4.5 billion years ends at a boundary about 60,000 kilometers above your head. Beyond that line, the sun is not filtered. It is not buffered. It is not moderated by anything except the hull of a spacecraft and the skill of the people who built it. The same sun that is firing this week, the one that still has fuel in that active region, the one that picked the equinox window, that sun does not take 2 weeks off. March 19th, 2026 is, on its own, just a date, a Tuesday. Nothing on the surface to distinguish it from any other late winter day on the calendar. But start stacking what we actually know about it, layer by layer, variable by variable, and something begins to feel different. Not in a conspiracy theory way, not in a the universe is sending us a message way. In a cold, physical, this is what the data actually shows way. And that's the kind of different that deserves your full attention. Start with the obvious. A coronal mass ejection is arriving from active region 4392, a sunspot group with a complex beta-gamma magnetic configuration, which is the classification reserved for regions with genuinely tangled, opposing magnetic polarities and real eruptive potential. This isn't a simple, clean sunspot that fired once and went quiet. It's a magnetically complicated structure that has already demonstrated it can produce significant eruptions. The CME it launched is traveling at over 1,200 kilometers per second. That's fast. Not record-breaking, but fast enough that the transit time from Sun to Earth is measured in hours rather than days. 33 hours to be specific. And the arrival window lands on March 19th. Now add the equinox geometry. The spring equinox falls on March 20th, 2026. One day after this, CME arrives. That single-day gap is not a comfortable buffer. It places the impact squarely inside what researchers who study seasonal geomagnetic patterns call the equinox window, the period during which the Russell-McLaren effect operates at peak efficiency. The geometry of Earth's magnetic axis relative to the incoming solar wind magnetic field reaches its most favorable coupling angle near the equinoxes. Favorable, in this context, means favorable for the storm. More energy transfers through. The shield that normally deflects or absorbs a significant portion of the solar wind's magnetic punch instead connects with it more cleanly. A storm that would behave one way, in July, arrives in late March and finds a door that's slightly more open than usual. Not wide open, just open enough to matter. Then add the radiation belt situation. The outer Van Allen belt has been running above alert thresholds for several consecutive days, elevated by the geomagnetic storm that moved through on March 13th and 14th. The 2 million electron-volt electron flux, the metric that satellite engineers actually monitor for deep dielectric charging risk, hasn't dropped back to baseline. The magnetosphere hasn't had time to exhale. The system that's about to absorb a new CME impact is not a rested, fully recovered system operating from a clean baseline. It's a system that's already carrying the energetic fingerprint of last week's event, still processing, still elevated, and now being asked to absorb a second impact before it finished dealing with the first. Stack all of that together. Complex active region, equinox geometry, preloaded radiation belts, incomplete magnetospheric recovery, and you have a convergence of conditions that, individually, each warrant attention. Simultaneously, they produce something that the standard G-scale forecast number simply cannot capture. The forecast is accurate. It is also, in a very real sense, a description of a single variable in a multivariable situation. Now here's the part that doesn't affect the space weather at all, but is genuinely hard to ignore from a purely human perspective. On the same day, March 19th, there are several near-Earth asteroid close approaches on the tracking schedule. Let me be completely clear. These asteroids pose no threat. Zero. They have no physical interaction with geomagnetic activity whatsoever. The orbital mechanics of rocky bodies and the magnetic coupling dynamics of solar plasma are entirely separate domains of physics. The asteroids are coincidence. Full stop. But here's the thing about human beings. We are pattern recognition machines. It's not a flaw. It's the cognitive architecture that kept our ancestors alive on a planet full of things that wanted to eat them. The brain is exquisitely tuned to notice when unusual things cluster in time, and it assigns meaning to that clustering, even when the clustering is entirely coincidental. Something is happening, the brain says, and in this specific case, that instinct isn't completely wrong. It's just pointed at the wrong phenomenon. Something is happening. It's happening in the magnetic field. The asteroids are just noise that happens to be scheduled on the same Tuesday. The pattern that genuinely deserves the attention your brain wants to give to the asteroid coincidence is the solar cycle pattern, and this one is not a coincidence at all. Solar cycle 25 was predicted by the official forecasting panel to be a modest cycle, below average potentially. The expected peak sunspot number was around 115, the kind of cycle that produces activity but doesn't rewrite any records. Those models were wrong, significantly wrong. The actual peak sunspot number came in at approximately 161, more than 40% above the forecast. The cycle produced more major flares, more fast CMEs, and more geomagnetic storm events than the quiet cycle the models anticipated. It overperformed at nearly every metric that space weather researchers use to characterize solar activity. And critically, it hasn't clearly entered its declining phase yet. The solar cycle doesn't end like a movie with a clean final scene. It winds down like a long, irregular fade. The transition from solar maximum towards solar minimum is not an abrupt cliff where activity drops to zero on a scheduled date. It's a slow slope, uneven and lumpy, with periods of renewed eruption frequency that can look, from the inside, almost indistinguishable from the maximum itself. We may still be on that slope. The data isn't conclusive yet, but the activity level we've been seeing in early 2026 is not the behavior of a sun that has clearly, definitively moved past its peak. There is a hypothesis sitting in the research literature, and this one I want to flag carefully as a direction of inquiry rather than established consensus, because intellectual honesty matters more than a dramatic narrative, that certain periods within solar cycles show event clustering that correlates loosely with orbital and seasonal patterns. The suggestion that mid-2025 through mid-2026 might represent a concentrated high-activity window within cycle 25 is not something you'll find in the official NOAA forecast documentation. But it's not being dismissed by researchers who study solar cycle behavior at the pattern level either. It occupies that interesting middle ground where the data is suggestive without being conclusive, which, if you've spent any time in science, you know is often where the most important questions live before they become answers. What we can say with considerably more confidence is this: equinox periods within high-activity solar cycles produce disproportionately concentrated records of significant geomagnetic storms. The storms happen year-round, obviously. The sun doesn't take the summer off. But when you sort historical geomagnetic storm records by month and by solar cycle phase, and look for clustering, the equinox windows inside active cycles stand out. The compound events, the ones with infrastructure consequences, the ones that make it into the engineering case studies and the post-event reports, they cluster here, not exclusively, but statistically, unmistakably. We are in one of those windows right now, and for the second time in a single week, a CME is inbound during it. That repetition matters, not because 2 moderate storms in a week necessarily equals catastrophe, they probably don't, but because the repetition itself is a data point about where we are in the activity envelope. We are not in a quiet interlude between cycles. We are in the active, elevated, still performing phase of a cycle that already surprised every model that tried to predict it. The question that surfaces repeatedly when you read deeply enough into the space weather research literature is one that doesn't yet have a clean answer. What happens when equinox geometry, radiation belt, preloading, CME stacking, magnetospheric memory, and solar cycle overperformance all align in the same event simultaneously? Not 2 of those factors, not 3, all of them, together, at once. Each factor is individually modeled. Each is understood in reasonable isolation. But the nonlinear interactions between all of them operating at the same time, the way a pre-stressed magnetosphere responds to a southward-oriented CME, arriving during peak equinox coupling efficiency during an overperforming solar cycle. That specific combination hasn't been seen frequently enough to build robust predictive models around it. The dataset doesn't exist yet, because the full alignment has been rare enough that when it does occur, it's as much a research event as it is a space weather event. Researchers are asking that question right now, actively. The answer isn't in yet, and the storm arriving in 33 hours is, in a very literal sense, a live experiment running on the largest magnetic laboratory available to science, the relationship between a middle-aged star and the small, magnetically shielded planet orbiting it at 1 astronomical unit. We are not just watching a storm arrive. We are watching the data being collected in real time. The kind of data that, a decade from now, might be cited in the paper that finally explains what happens when all the conditions align at once. We just happen to be living inside the experiment while it runs. Here's something that should actually reassure you, because not everything in this story is ominous, and I think it's important to say that clearly before we go any further. The space weather community has a communication problem that runs in both directions. Sometimes the risk gets undersold, context gets stripped out, variables get ignored, and a genuinely complex situation gets flattened into a single classification number that tells you almost nothing useful. But sometimes the risk gets oversold too. Dramatic headlines, worst-case framings, stock footage of solar flares accompanied by music that sounds like the end of a Marvel film. Both failures erode trust. And trust in accurate science communication is something we genuinely cannot afford to lose when the stakes are real. So let's be honest about the most probable outcome of this specific event. Based on current forecasts, the likeliest result of this storm is a strong, potentially spectacular aurora display, visible at latitudes considerably lower than usual. People in the northern United States, across Central Europe, in parts of New Zealand and southern Australia, people who rarely or never see the aurora may step outside on the night of March 19th or 20th and watch the sky do something genuinely extraordinary. Green and red curtains of light moving across latitudes where they almost never appear. That is not a consolation prize. That is one of the most visually stunning phenomena the natural world produces, and this storm may deliver it to tens of millions of people who have never experienced it. If that's the main outcome, the storm will have done something beautiful. Beyond the auroras, some satellite operators will observe anomalous behavior in their systems and respond according to their existing contingency procedures. There may be brief high-frequency radio communication disruptions at polar and high-latitude regions, the kind that affect some aviation communication and amateur radio operators, but resolve within hours. There may be minor GPS accuracy degradation in polar regions, the kind that causes navigational systems to flag reduced confidence rather than fail outright. Airlines flying polar routes, which are common on trans-Pacific and transatlantic long-haul flights, may reroute slightly to maintain reliable communication links and reduce crew radiation exposure. These are real operational responses to real conditions. They are also entirely routine. Airline dispatchers and satellite operations teams have playbooks for exactly this situation. They will execute those playbooks. Flights will land. Satellites will keep functioning. For the average person on the ground, the direct and immediate impact of a G2 or G3 geomagnetic event is, measured honestly, close to zero. Your phone works. The power stays on. The internet continues to route traffic. The payment systems process transactions. The storm moves through. The measurements spike. The auroras light up the high latitudes. And then it fades over the following day or two. The magnetosphere absorbs the impact. The radiation belts gradually relax, back toward baseline, and the next news cycle moves on to something else entirely. That is the most probable outcome of this specific event, and it deserves to be stated without qualification, because accurate risk communication requires acknowledging when the likely answer is probably fine. But here's the reframe that actually matters, and it's the one I want you to carry out of this video, rather than a vague sense of alarm. This specific storm probably won't cause a crisis. The pattern it is part of might be telling us something genuinely important about how we think about space weather risk, and whether the tools we currently use to communicate that risk are adequate for the world we actually live in. What this week represents, the compound storms, the equinox timing, the elevated radiation belts, the pre-stressed magnetosphere, the overperforming solar cycle, is a convergence of conditions that researchers have been arguing for years should be tracked holistically, rather than as a collection of independent variables. The equinox effect is not new science. Russell and McFerrin published their foundational paper in 1973. That's more than 50 years ago. The concept of magnetospheric memory, the idea that the system carries residual energy and stress from prior events that influences how it responds to subsequent impacts, is not a fringe hypothesis. It's documented in the peer-reviewed space weather literature. The statistical clustering of major geomagnetic storms around equinox windows is visible in 5 decades of historical data if you simply plot the events by calendar month and look at the result. The risks of deep dielectric charging from elevated 2 million electron-volt electron flux are well understood by the satellite engineering community, well enough that it has its own alert threshold managed by NOAA's Space Weather Prediction Center. None of this is secret. None of it is obscure in the sense of being unavailable. It lives in the scientific literature, in the engineering guidelines, in the operational manuals of the organizations that actually run space-based infrastructure. The problem isn't that the knowledge doesn't exist. The problem is that it isn't synthesized, pulled together into a single, accessible, contextual alert that says, here are the 5 variables that matter right now. Here is how they interact. And here is why this particular combination warrants more attention than the headline number suggests. That synthesis doesn't exist in any public-facing tool currently available. You cannot look it up on your phone. You cannot find it in the NOAA alerts. The G-scale number is there. The individual data streams are there if you know where to look and how to read them. But the integrated picture, the compound risk assessment that accounts for season, prior event state, radiation environment, and solar cycle phase simultaneously, that picture has to be assembled manually by people who know what they're looking for. That gap is the real story. Not this storm specifically, not March 19th, 2026, as a uniquely catastrophic date, but the systematic mismatch between what the scientific community understands about context-dependent, compound space weather risk, and what the public alert infrastructure currently communicates to the people and organizations who depend on it. A G-scale number issued in isolation, stripped of seasonal context, with no reference to magnetospheric recovery state, no radiation belt status, no solar cycle phase annotation, that number is true as far as it goes. It is also in any situation where multiple variables are simultaneously elevated, profoundly incomplete. It answers a narrow question accurately, while leaving the broader question entirely unaddressed. Think about how we communicate terrestrial weather risk and how far that field has come in the last 30 years. Modern weather forecasting doesn't just tell you it will rain. It tells you accumulated rainfall totals, soil saturation levels, flood stage on local rivers, wind speed at multiple altitudes, lightning probability, and severe weather timing windows, all integrated into a single forecast product that a non-specialist can interpret in 30 seconds. Space weather communication for the general public is still essentially at the it might rain stage. The underlying science has advanced enormously. The public-facing communication hasn't kept pace. And as our technological infrastructure becomes more space-dependent, more satellites, more GPS-reliant navigation, more power grid nodes at high latitudes, more commercial human spaceflight, the cost of that communication gap increases. The equinox arrives twice every year. March and September, fixed, orbital, mathematical, non-negotiable. It will happen again in 6 months, and solar cycle 25 hasn't finished. The active regions will keep emerging, rotating into the Earth-facing window, and firing. Some of those firings will coincide with equinox windows. Some will arrive at magnetospheres already stressed by prior events. Some will find Earth's field in the most geometrically vulnerable orientation it reaches all year. And when those things align together, the way they have aligned this week, the outcome will not be adequately described by a single letter and a number on a 5-point scale that was designed to communicate storm intensity without reference to any of the contextual variables that determine actual impact. What comes next, over the months and years ahead as solar cycle 25 completes its arc and the research community continues developing better compound risk models, is the part of this story that actually determines whether the infrastructure civilization depends on is prepared for the right kind of storm. Not just the biggest one. Not just the G5 that makes every headline and dominates the disaster planning scenarios. The precisely timed one. The second storm in a week. The moderate event that arrives when the system is already stressed during the equinox window, with the radiation belts preloaded and the magnetosphere running on insufficient recovery time. That event doesn't have a dramatic name. It doesn't get a Hollywood disaster film. But it is, in several measurable ways, the more insidious threat, because it operates below the threshold of public alarm, while exploiting every contextual vulnerability the standard alert system doesn't account for. The sun doesn't schedule around us. It has been doing this for 4.5 billion years, and it will keep doing it for another 5 billion after we're gone. It doesn't check the equinox calendar before firing. It doesn't wait for the magnetosphere to recover before launching a second CME. It doesn't know that 4 astronauts are scheduled to leave Earth's magnetic protection in 2 weeks. It just fires when the physics tells it to fire, and the consequences land wherever the geometry and the timing determine they land. But we can schedule around it. We can build forecasting tools that account for the full variable set. We can communicate risk in context rather than in isolation. We can treat compound space weather events as the complex, multivariable phenomena they actually are, rather than flattening them into a single number that loses almost everything important in the translation. Because the biggest storm isn't the only threat. The most precisely timed one, arriving into the right combination of pre-existing conditions during the right window in the orbital calendar, might be considerably worse than its classification suggests. And the gap between what the classification says and what the physics means, that gap is exactly where the risk lives. That's what this week is showing us. Not through catastrophe, through the quiet accumulation of conditions that the standard tools weren't built to see all at once.